Hello everyone. Today I am going to give my presentation on post-route QR estimates of HLS designs using machine learning. In this work, we have predicted the post-route resource requirement, latency, timing, and area of a HLS design just by looking into the high-level C++ or System C code or without performing any kind of C synthesis or logic synthesis. So, about myself, I am Pingaksha Goswami. I am a PhD student in the Department of Electrical Engineering in University of Texas, Dallas. My research interests include machine learning based prediction in FPGA CAD, FPGA prototyping, and hardware accelerator design using FPGA. Now let's go over the high-level synthesis design flow. Traditionally, the design entry into high-level synthesis tools, design entry to is logic synthesis tool is in hardware description languages like Verilog, VHDL, or System Verilog. But as the designs are becoming more complex and the designs are becoming more complex and the level of abstraction has gone up. Nowadays, the design entry to the tool is written in high algorithmic level in high level languages like C, C++, or System C. In this slide, I have shown how a high-level language written in C, C++, or System C is converted into RTL and finally it goes through the physical design flow. So initially the high-level HLS code written in C, C++ or System C is compiled using a compiler called LLVM IR. Then the HLS tool performs resource allocation, scheduling, and binding to generate RTL code. And finally, the RTL code passes through the physical design flow consisting of logic synthesis, technology mapping, optimization, placement, and routing. Now let's see what is high-level synthesis. High-level synthesis is the technology by which a program or a hardware design written in high-level languages like C, C++, or System C is converted into a synthesizable RTL code. This is the flow for HLS to RTL. It consists of three main stages: resource allocation, scheduling, and binding before generating the RTL design. These are some of the popular HLS tools available in the market. In our research, we have used Xilinx Vivado HLS as our preferred HLS tools. And for the rest of my presentation, all the results and descriptions described in the presentation will use Vivado HLS. As I have shown in the previous slide, the process of conversion of a HLS design into RTL and finally the physical design flow is extremely complex and it consists of number of stages. In order to show the complexity of the flow, we have mapped a complex design called ADPCM or Adaptive Differential Pulse Code Modulation into Xilinx Zinc Ultrascale Plus FPGA device. The design consists of one top module and 11 sub-functions. It consists of 12 loops, 9 arrays, and 11 functions. And if we apply pragmas or optimization, it consists of a design space which is more than 100,000. So this is the runtime of this design. So it consists of C synthesis, logic synthesis, and place and route. The C synthesis time here includes the design space exploration time of around 500 designs. And finally, we select only one design out of those 500 designs for our physical implementation consisting of logic synthesis and place and route. And the total time for in order to generate one design is around 3500 minutes. But sometimes the results after the place and route stage may not match the results reported after C synthesis stage. In this case, we may have to perform this process again and we have to repeat this test multiple times. Hence, it is a time-consuming process. Now, let's see how the quality of a design is measured in ASIC or FPGA. In case of any ASIC or FPGA based design, the quality is measured in terms of latency, area, timing, or power. In case of FPGA, area is measured in terms of FPGA resources like flip-flops, LUT, block RAM, DSP, and IOBs. Timing is the critical path of the circuit on which the maximum operating frequency of the circuit depends on. And power, there are two types of power, dynamic power and static power. In our research, we have predicted only latency, resource requirement, and timing, but not power, because in order to generate the labels for power, we have to run it on actual hardware, and running around 6,000 to 7,000 training design on hardware was practically not possible. Hence, our prediction is limited only to latency, resource requirement, and timing. Now, let's see the necessity to come up with this research. Generally, during design space exploration, the designer does not perform logic synthesis or place and route. He simply performs C synthesis on the results to generate quick estimates how long will it take each version of the design what is the performance of each design for in terms of area, resource requirement, and timing. But the results reported by the Vivado HLS tool after C synthesis stage is highly inaccurate. This is shown in this particular graph. As you can see, there are two graphs, two bars, the orange color one and the green color one. The orange bar shows the Vivado C synthesis estimate, and the green color one shows the actual post route values for LUT, clock period, block RAM, and DSP. The Vivado HLS tool highly overestimate both the resource requirement and timing after C synthesis stage, which is obvious from this particular diagram. Now, if the designer relies on the Vivado C synthesis values to guide his design space explorer, he may not always end up with the most optimized design, and it may misguide him. So one of the major focus of this research is to help the designer to get a pretty accurate estimates of his values right after before the C synthesis stage itself. There are certain recent work which predicts the post-route QR of HLS designs using machine learning or analytical method. One of the popular work called fast and accurate estimation of HLS design. In this work, the authors analyze the post-C synthesis log files to extract features and create machine learning model to predict the post-route latency, post-route resource requirement, and timing. The drawback of this work is that in order to generate the features, the designer have to perform C synthesis on the design. Another work called COMBA, in which the authors predict the post-route latency and resource requirement of the design by performing analytical using analytical method on the LLVM data flow and data flow graphs, control and data flow graph. But the major drawback of this work is this work compares their result against the Vivado C synthesis results, which itself is highly inaccurate. Another work called Pyramid HLS is similar to the first one, where the authors analyze the C synthesis log files to predict post-route resource requirement and timing. Finally, we have Iron Man, where the author predict the post-route resource and frequency by using graph neural network on the LLVM control and data flow graph. But the drawback of this work is that they have used only one pragmas, whether to use DSP block or not, in their design space exploration, and they uses a code transformer to generate the features. The major drawback of these four works I have discussed is none of these four works can predict the all three vital FPGA parameters together, and also all these four works require some kind of synthesis to generate the labels. in order to address this drawback, in our work we predict the post-route resource requirement, latency and clock period without performing any kind of C synthesis or logic synthesis, just by looking into the high level C++ code, and our level is our value or the predicted target values are after the post-route values. Now this is the problem statement. In this work we are given a set of synthesizable C++ code along with the pragma settings like loop unrolling, array partitioning, etc. We have to come up with a methodology by which we can predict the post-route resource requirement, latency and timing of the design without actually synthesizing the design in real time. Now I have been discussing about LLVM. Let's see what is LLVM. LLVM is a compiler which is very similar to GCC. GCC which converts a high-level code written in C, C++ or Python into a processor-independent assembly language code known as intermediate representation. LLVM consists of three parts: the front-end parser, which called Clang, which parses the C++ code and generates an unoptimized intermediate representation code or IR code. There is a middle-end optimizer which performs optimization like redundant code removal, memory optimization, bit width reduction, loop merging, unnecessary loop removal, etc. to generate an optimized IR, and this optimized IR is read by the technology specific backend to generate ARM assembly or GPU specific assembly language code. In our work or in FPGA in general, we directly perform operation on the IR code to generate the RTL code or various graphs which are discussed later. This is our proposed flow. Just like any other machine learning model, in our work also it has two parts: the features and the training data has two parts: the features and the labels. The features come from four different sources: the high level C++ code, LLVM, IR code and the graphs, and the labels comes from the post-route values. In order to generate the labels, we pass the same set of C++ code into the FPGA HLS flow and the physical design flow to generate the label and create the machine learning model. Now, whenever a new design comes, we simply convert the new C++ code into LLVM IR code and the corresponding graphs to extract the features and pass it to the trained model to generate the post-route latency, resource requirement and clock period. The advantage of this work is the process of converting a C++ code into LLVM IR code is very fast. For example, in order to generate LLVM IR code and graphs for 100 C++ code, it takes less than 10 seconds, which is less than 1 second for each design. These are our four different feature sources: high-level C++ code, IR code, control flow graph, and call graph. Most of our features comes from the LLVM IR code, where we perform a microcode analysis to see the number of instructions in each basic block. Basic blocks are nothing but a continuous sequence of assembly language code which are branched at if-else condition, function returns, or loops. Other sorts of features include the high-level C++ code, where we analyze the pragmas like the level of loops, number of loops unroll, loop pipeline initiation, interval, array partitioning factors, etc. From control flow graph is nothing but a continuous connection of basic blocks. So we analyze the control flow graph to see total number of nodes in each basic block, in each control flow graph, number of functional unit, critical path length, etc. And call graph represents the interfunctional relationship between the functions. So these are the different types of three different types of graphs from which we have extracted the features. Call graph shows the interfunction relationship, control flow graph shows the inter-basic block relationship, and data flow graph shows how the data is passed inside its basic block. We performed a critical study on feature importance using a tool called XGBoost plot importance, and it has been found that LLVM IR code holds the most importance for all the three predicted parameters for the type of data we have. This is because from out of the 69 features, we have extracted 44 features from the LLVM IR code. Hence, LLVM IR code holds the most importance among all the features. Now, let's see how we selected the training data. In order to select the training data, we performed an experiment where we combined different designs from different designs to create a data set of around 400 designs. Then we changed the training data set gradually from 20% to maximum of 80%. Now, in order to have a balance between training time and accuracy, we measured the R square value and plotted it here. And it has been found that if we use 30% of the data for training, we get R square value above 0.9 for clock period and for clock period and LUT and 0.75 for latency. We created four different regression model: linear regression, multi-layer perceptron regression, random forest, and gradient boost, and calculated the mean absolute percentage error. It has been found that gradient boost gives us the best error, minimum error or the best result, and hence for rest of the presentation we use gradient boost as our preferred machine learning model. For your reference, I have also plotted the error reported by Vivado HLS after C synthesis test, which is very high. In order to test the robustness of our model, we created three different experiments. In the first experiment, we used 10 different benchmark from the CH2 and CH stone and S2C benchmark and created a 10 different machine learning model where 30% of the designs were used for training and 70% were used for testing using the gradient boost regression method. In the next experiment, we perform frequency sweep where we check the performance of our model on different frequency. In this experiment, we created a dataset of around 300 designs consisting of 100 designs from three different frequencies: 100 megahertz, 150 megahertz, and 200 megahertz. Later, we created a baseline design from 8 different frequencies and predict on them. Here, baseline design means the designs which does not have any pragmas. Finally, in order to test the robustness of our model, we mapped the ADPCM, which is the most complex design among all the designs we have, into three different Xilinx FPGAs and then tested on 64 totally new unseen designs. These are the results. So here for the first experiment, fully localized training method, we measured the accuracy performance using mean absolute percentage error. For your reference, I have also plotted the error reported by Vivado after the C-synthesis test. As we can see, we get less than 10 average, less than 10% error for all the three predicted parameters. And in some cases, we get close to zero error for clock period and resources. In the next experiment, we performed a frequency sweep experiment where we trained on three different frequencies: 100 megahertz, 150 megahertz, and 200 megahertz, where we generated around 100 different versions for each of the three frequencies by performing design space exploration and changing the pragmas. And we predict on 8 different frequencies. Here, instead of mean absolute percentage error, we have plotted the actual values reported by our tool using the machine learning model. As you can see, the values reported by our tool after the machine learning model closely correlates the values reported after post-route values or after routing. We also ran experiments beyond 500 megahertz but it has been found that the value reported by 500 megahertz after by the Vivado HLS tool remains more or less constant, and the tool crashes after 800 megahertz. Basically, it cannot synthesize beyond 800 megahertz. Finally, in order to test the robustness of our model, we used the ADPCM, which is the most complex design among all the designs on three different Xilinx FPGAs: Zinc, Vertex, and Kintex. So we trained on 300 designs and predicted on 64 different designs. And our for clock period, our mean absolute percentage error is less than 8%. For latency and LUT, it is slightly higher because the range of latency and LUT are significantly larger as compared to clock period. Latency for LUT ADPCM lies between a minimum of few hundreds to a maximum of millions of clock cycle, while LUT lies from minimum of few thousands to maximum of around 600,000. Hence the range is very large. Hence the accuracy is little bit less. But it has been found experimentally that if a model works on ADPCM, it will work on all the other 9 benchmarks we have. This is the conclusion. This is the first work where the post-route QR has been predicted using machine learning without performing any kind of logic synthesis or C synthesis. We tested on 10 different benchmarks taken from CH-Stone and S2C bench. Our work can be easily integrated with commercial HLS tools like Vivado HLS and NEC Cyber Workbench. We achieved mean absolute error of less than 10% for all the three predicted parameters using all the three predicted methods. We also achieved a speed up of 3.48 times using the fully localized training method as compared to Vivado HLS. Finally, the robustness of our work is tested on multiple frequency design and multiple FPGA devices. These are our contacts. You can contact us for more details. Thank you.